In this video, I will give you an introduction to methods that we frequently use in electrostatics. Now, the goal, whenever we have a problem in electrostatics that we want to solve, typically what we want to obtain is either the electric field or the potential. If you're interested in predicting the motion, then we're dealing with probably Newton's second law, meaning you need to know the electric forces. And to find the electric forces in order to predict the motion, then you will need to know what is the electric field. So if you want to predict the motion, then what you need is to solve Newton's second law, and since we're dealing with electric forces, you will need to know what is the electric field. Now, if you have a different kind of problem and energy is useful, and you don't need to predict the motion of the system, if you're only interested in the initial and the final state of your system, then using the energy conservation principle will probably do it for your problem. And energy, electric potential energy, to calculate this quantity, it will be sufficient for you to know the electric potential, V. Now, we do know that the electric field and the potential are related. We also know that the electric field, the three components of the electric field, actually they are not entirely independent of each other. They do include some redundancy. And this is why it is easier if you work with potential. Potential is a single number. There is no redundancy, and all the information we need is included here. You can obtain the electric field, the vector, if you know the potential everywhere in space. So the goal in electrostatics is to find the electric field or to find potential, and if you can do your work with potential, that's even better. It makes your life easier. Now, frequently though, I would say in most cases, really, there is no way you can obtain an analytic solution for the electric field or the potential. And of course, as with the majority of problems in physics, we rely on numerical calculations to solve the problems. And this means we need to have approaches that allow us to obtain these two quantities related with electrostatics. In this chapter, about half of the chapter on potentials is devoted in finding the electric potential. And to do that, the method that we use is to solve either Poisson's equations or Laplace equation. All right. Now, Poisson's equation says that the Laplacian of the potential is equal to minus the charge density over epsilon naught. Now, Laplace's equation is really Poisson's equation when the charge density is 0. So obviously if you plug in a 0 here, you get that the Laplacian of the potential is 0. Now, for the problems that we will see, so the general form is Poisson's equation. Now, for the problems that we will see, the goal will be to find potential, but in areas where there is no charge density. There is some charge somewhere near, but not where we want to find the electric potential at. So the goal for us will be to solve Laplace's equation. Now, there is an important theorem, the first uniqueness theorem, that says if if you specify, if you know what the potential is on the surface of a volume, then the potential is uniquely determined. And what this means, okay, if you set the potential on the surface of your volume, then there is only one physical situation that can give you that potential on the surface. So that means when you solve your Laplace's equation with a fixed potential on the surface of your volume, if you find what the potential is in that volume, you have found the only possible physical situation for potential. Okay, and this is important. Imagine that the first uniqueness theorem was not true. Then, if there are two possible potential solutions for potential in the volume that you're interested in, and you find one of them, how do you know? There's no way for you to know what's gonna take place in reality. So the first uniqueness theorem is very important. Okay, it allows us actually to solve Laplace's equation, find the solution, and have confidence that this is what happens in reality. Right. Now, Laplace's equation includes the Laplacian, and we have seen so far, we need to use different coordinate systems. In the Cartesian coordinate system, you have the second partial derivative with respect to x plus the second partial derivative with respect to y, and the same thing in the z. In the cylindrical coordinate system, you have something a little bit more complicated. And in the spherical coordinate system, you have something even more complicated. It actually doesn't even fit here. So the entire Laplacian goes all the way to here. Now, I will mention this again as we're solving problems, but one thing that I want you to pay attention, the Laplacian in the Cartesian coordinate system, okay, fairly simple, okay, just the second partial derivative with respect to x, Now, when you get to the Laplacian in cylindrical and spherical coordinate systems, pay attention to the following. Here, you have a term, s times the partial of potential in our case with respect to s. And then you have parentheses. And then outside of the parentheses, you have another partial with respect to s. Okay, here, when you do your calculations, you will take the partial of a product. And remember to keep this in mind. When you take the derivative of a product, you need, in this case there are two terms, you will be getting two terms, right? The derivative of the first term times the second term plus the first term times the derivative of the second term. Okay. So keep in mind, here you're taking the derivative of a product, and in the spherical coordinate system, you will be doing this more than once. You have one here and one here, and thankfully we don't have that again over here. All right, so these equations are found. You have a PDF from me that includes the Laplacian in these three coordinate systems, and also you can find them in the book. Now, all right. So these are the Laplacians. Now I want to give you an idea for what the problems that you will solve. What will be the the main, the main approach and what will be the main problem setup. What the problem will tell you is that you, first of all, that you will need to find the potential in an area with no charge density. This means you will need to solve Laplace's equation. Now, the problem will also specify, they will tell you what is the potential on the surface. And by doing that, you will have confidence that once you find the potential in that volume, you found the physical situation that you're looking for. Now, depending on the problem, you will need to choose a coordinate system, as we almost always do. Depending on what coordinate system you choose, you will have an expression for the Laplacian. Okay, you will have to use one of the three. And once you have written once you've written down the Laplacian in your coordinate system, then you start solving the problem while at the same time implementing the boundary conditions. Okay, when we specify the potential on the surface, we call this the boundary condition. So your goal will be to solve Laplace's equation for potential and your coordinate system while making sure that the boundary conditions are obeyed. And that will give you, at the end, your goal, of course, will be to have the potential in your coordinate system for the volume that you're interested in.